It's dot 6 p.m.
Yes.
Should we start?
I think we can start now.
Okay. So welcome everybody to this evening, India time evening plenary talk by Professor Mark Wilde. And, it's probably 8:30 a.m. Mark's time. So I really wanted to thank him for starting up early for us. I also wanted to congratulate the conference organizers for getting such a spectacular, really galaxy of speakers from all over the world. As usual, every year, without fail, we are doing. So I'll not, this session, the first talk has 1 hour, time, but I would like maybe 45, 50 minutes, the talk gets over, and then we'll have some time for a discussion if Mark allows. So very quickly, I don't want to stand between the speaker and my introduction. You can always look him up at the conference website as well. Just for completeness, PhD in electrical engineering, I think in 2008, from the University of Southern California. Mark is currently an associate professor at Cornell University. Typical of people who are working here in this area, his department is electrical and computer engineering. So I think it just describes in some way how it's doing and how interdisciplinary and transdisciplinary this field is becoming. He's also a Fields member in the School of Applied and Engineering Physics and the Department of Computer Science at Cornell. So he's a recipient of National Science Foundation Career Development Award a few years back. He's a co-recipient of the 2018 AHP Berkhauser Prize. And I saw that he's an outstanding referee of the American Physical Society. Kind of questions that he would be addressing, the screen, already you can see one that he'll be talking to us about. But what are the ultimate limits that nature imposes on communication and computation? And what are the effective procedures for achieving these limits? So this is what he has been doing. I've seen some notable papers with QIQT Guha, PRL maybe in 2012, then 2014 paper, but it's really a remarkable journey. So Mark, over to you, maybe 45, 50 minutes for this talk, and looking forward to this. Thank you.
Sure. Thanks for the very nice introduction. I'm happy to present and to be here. I'm actually in Louisiana right now, so it's 7:30 a.m.
Wow.
It's the end of but it's fine. I wake up at like 6 a.m. usually.
Okay.
It's the end of the semester at Cornell, and so I'm actually from Louisiana, so I'm back home in my parents' house visiting family. And I'll be going to some. I was formerly a professor at Louisiana State University for a decade, since 2013, and then in last year, 2022, I moved to Cornell, and I've been liking it there. Of course, it's very different climates. Louisiana's hot and humid, and Cornell is frigid during the winter, as you know from being in Rochester.
Yes.
Okay, so yeah, you were speaking about the interdisciplinary nature of this field. That is something that has been a hallmark of what I've been doing since graduate school. So I got my degree in electrical engineering. My PhD advisor was a physicist, Todd Brunn at Southern California. And then I did a postdoc at McGill in the School of Computer Science. My postdoc advisor was also a physicist, Patrick Hayden, who's now moved to Stanford, and he's doing things with high energy physics. You should try to get him to speak. He would be a fantastic speaker. And then at LSU, I was in the Department of Physics and Astronomy. So, and then when I moved to Cornell, I came sort of back home to my PhD department, electrical engineering. And that's been a really great aspect of this field, is the opportunity to interact with so many people coming from different backgrounds in computer science, engineering, physics, and also mathematics. You know, I never myself had an appointment in mathematics, but several of my colleagues do. Okay, so that being said, I'm going to tell you about recent work with Ludovico Lamy. We were fortunate, and this got published in Nature Photonics recently. Okay, so the topic is we solved the quantum and private capacities of a particular class of bosonic channels called bosonic dephasing channels. What's notable about this class of channels is that they're non-Gaussian, and so they're somehow outside of the usual class of channels that people have considered in quantum information. And that being said, I'm going to plug a book of on this topic. Alessio Serafini wrote a very excellent textbook on the topic of bosonic Gaussian quantum information, if people want to have more background on this topic. I taught a course about it when I was at LSU in spring 2019. At some point at Cornell, I'd like to teach it again. Okay, so let's get into it. This is a talk that Ludovico prepared these slides. He presented at the QIP conference. It was a half-hour talk, but we can have like extended discussions and questions, and possibly that will occupy the full 45 to 50 minutes. And anyone should feel free to interrupt me at any point with questions. I'm happy to address and have discussions. Okay, so to motivate the model of this channel, we can imagine this kind of picture that Ludovico drew of light rays traveling along an optical fiber. And when it's traveling, different rays will take different paths. And when they do so, they accumulate different phases, okay? And the precise phase that's accumulated may not be known. And so then the best thing we can do is describe them by a probability distribution, okay? So this is the mathematical model of the bosonic dephasing channel. What's going on here? Suppose that this probability distribution is not here, and we're just focusing on this term right here. Then what this is saying is an input quantum state described by the density operator rho undergoes a unitary evolution described by the phase phi, okay? And this is a bosonic state, so we can, this is going to be a single mode bosonic state right now. Later on, we can generalize it to multiple modes. And so this describes the phase that the bosonic state will undergo. You know, if it's a coherent state, rho described by the parameter alpha, then after this phase occurs, the state will be alpha described by alpha e to the I phi. So it accumulates a phase. But you know, we're saying that we don't know which particular phase it undergoes, but through repetition experiment, we could describe the phase that's accumulated in terms of a probability distribution. Okay, so this is saying that the output state will be a mixture of these different phase rotated states. So that's the bosonic dephasing channel. And just to, you know, reiterate what I was saying, rho is an input state, phi is the random phase. This right here is the photon number Hamiltonian, the photon number operator, and that describes which phase will occur. Okay, so that's the channel. And as I said in the beginning, it is not a Gaussian channel. What is a Gaussian channel? It's one that would take a Gaussian state to a Gaussian state. And what's nice about Gaussian states is that they're described in terms of just a few parameters, the mean vector and covariance matrix. And so they're easier to work with for that purpose. There's many researchers in India who have worked on Gaussian quantum information, Gaussian states, etc. Some names that come to mind are K.R. Parthasarathi, Simon, I've seen his name, and many others. Okay. So, and a recent person who who's more my age is Krishna Kumar Savapathy. He did his PhD, I think, with Simon. Okay. So what are examples of this probability distribution? One is which we call the wrapped normal distribution. So as you know, the normal distribution, its support is on the full real line, but these phases are just on the unit circle. So we can imagine, like, if the mean of this Gaussian distribution is 0 and its variance is gamma, this is a picture of what that distribution would look like. So it has most of the probability mass around phi equals 0, and then it has reduced mass, and the Gaussian is on the real line, and so the mass will be, as you decay, it'll still have mass, but it'll be far less weight, but it'll sort of circle around an infinite number of times. So that's what this is saying. Okay, that's called wrapped normal distribution. That's a key example that we'll consider throughout this talk, in work prior to ours by Stefano Mancini and collaborators. That was the model that they considered. This paper is one that came prior to ours, which, you know, it made some important observations about the bosonic dephasing channel, did some numerics to describe the capacity. What our work did was it gave an analytical solution to this problem. And later on, we'll discuss the precise result. Okay, so for some backgrounds, let's talk about bosonic systems. A single mode bosonic state Hilbert space is spanned by the Fock states, which are just the orthonormal basis that goes from 0 photons, 1 photon, all the way up to an infinite number of photons. The photon number Hamiltonian is such that these Fock states, these also called photon number states, are eigenstates of the photon of this Hamiltonian. And when the photon number operator acts on these photon number states, the eigenvalue is the number of photons in the state. Okay, so the state of, this is saying that an n photon number state has n photons. And thus we can write it in this other way as well as an operator. Okay. The other thing we'll have to think about is how to represent states in the photon number basis. You can really just think of it as an infinite matrix. These are the elements. The diagonal elements form a probability distribution that some that are non-negative and some to 1. And these off-diagonal elements represent coherences. So these terms represent superpositions of, terms related to what's called coherences, and what's related to like superposition of 0 and 1 photon numbers, superposition of 0 and 2 photon numbers, etc. Okay. Now, so thinking about the bosonic dephasing channel, one thing we have to think about is how does it act on the elements, the individual elements of this matrix. Okay, so to determine that, we should determine how the channel acts on this term, and ket n bra m. And then due to linearity, if we can figure out how it acts on these terms, we can figure out how it acts on the whole density matrix. Okay, So we take the model of the channel that I talked about before, and we just apply it to this element. And using what we just discussed, when A dagger A acts on N, we'll get a scalar N for this term. And then when this A dagger A acts on M, we'll get M up here. And then you combine them together and you get this term here. So this is very interesting. This is a Fourier transform of this probability distribution. In electrical engineering theory, this would be called, electrical engineering systems theory, this would be called inverse discrete time Fourier transform, because in this domain, the variable is discrete, but in the Fourier domain, the parameter is continuous. Okay. So now, when you study this term, you see that we integrate over phi. It's a function of these two integers, n and m, which we can think about as indices of a matrix, indices of an infinite matrix, okay? And so that matrix is what I'm calling T. We're calling it T because later we're going to see that it's a Toeplitz matrix, okay? And so there's a particular definition of that I'll give in a minute. And it's a function of the particular distribution that's being used. But what you see is that for any possible distribution you input here, the resulting matrix what we will see is that it's a Toeplitz matrix. Okay. So now, when this channel, now we figured out how it acts on these terms. And then what I said is that due to linearity, we can figure out how it will act on a general density matrix representing the Fock basis. And what you see is that the individual terms of the density matrix get multiplied by the terms of this Toeplitz matrix. So the 0,0 entry of the density matrix gets multiplied by the 0,0 entry of the Toeplitz matrix. And more generally, the n-mth entry of the density matrix gets multiplied by the n-mth entry of the Toeplitz matrix. That is a particular kind of matrix multiplication, which is different from the usual one. That's called, it's element-wise multiplication. That's called the Schur product or the Hadamard product, okay? And these kinds of channels where the input density matrix, you take it and perform the entry-wise product with another matrix, those have been studied before extensively. They're called Hadamard channels. I wrote a textbook on quantum information theory, and those are important. Those are an important class of channels that are studied, and they're very fascinating. The paper that was mentioned that I published with QIQT Guha in 2012, some of those bosonic channels are also Hadamard channels. In fact, like this is kind of a side discussion of a pure amplifier channel is a kind of Hadamard channel, and they have been studied in different papers. Okay, so a matrix is a Toeplitz matrix if the n-mth entry is just a simple function of the difference of the indices n and m, okay? And then you see that here, right? This whole thing is a function of the difference of n and m, so therefore it's a Toeplitz matrix. And that observation is critical and allows us to bring in tools that have been used to study Toeplitz matrices and their properties. And there's a very important theorem that we'll invoke called Sago theorem, which allows you to understand the asymptotic properties of this infinite dimensional matrix. So that's one of the key tools that we use to derive our results. Okay, and as the example that we discussed before, if you take as the probability distribution the wrapped normal distribution we said that's a Gaussian. And so, one thing that's well known about Gaussians is that the Fourier transform of a Gaussian is also a Gaussian. And that kind of result continues to hold even for the wrapped normal distribution. Okay. So this matrix is a Toeplitz matrix. And it's a particular, it's like, we call it like a Gaussian Toeplitz matrix. Okay. So what do we want to use this channel for? We want to use it for communication. Okay. And so this is a kind of standard diagram that describes quantum communication. So what's going on here is the channel N, you're allowed to use it many times. Okay. And often we say the channel big N is allowed to be used little n times. Okay. And before using the channel, you're allowed to do an encoding and a decoding. In quantum Shannon theory, in quantum information theory, when the goal is to understand the fundamental limits, we don't make any constraints on the computational power of the encoding and the decoding. We assume that you can do whatever is allowed by the laws of quantum mechanics. And so most generally, this encoding is allowed to be a completely positive trace preserving map or a quantum channel on its own, and the same here. Okay. And then the goal is to use the encoding, the decoding, the channel to communicate one share of a possibly entangled state with a reference system from Alice, who's here, to Bob, who's over here. Okay. And so, effectively, that is what's happening in our communication right now from New Orleans to India. Okay. Except the communication we're doing now is classical. Much more difficult is to communicate quantum data. That I would say does not really in this kind of advanced form that we want exist yet. That's something that experiments are striving to do. So how do we quantify performance of the communication scheme? Well, at the end of the process, there's going to be a state generated by the receiver, Bob, and the reference system doesn't undergo any transformation, but this system M is the one that undergoes the transformation. And so the goal is for this state to be approximately close to this one, such that as the number of channel uses increases, the error in the communication goes to zero. And a simple way to quantify error is in terms of fidelity. Okay. And then the other performance criterion is the rate. How many qubits can you transmit per channel use? So the channel is being used little n times. The number of qubits being transmitted is the binary logarithm of this, the dimension of this Hilbert space. As an example, if this had a dimension 8, the number of qubits for that Hilbert space would be 3. And the rate is number of qubits per channel use. So then the capacity is defined. So a rate is described to be achievable if there exists a sequence of encodings and decodings such that the error is tending to 0 and the rate is converging or stays constant at this value R. Okay. And then the capacity of the channel is the largest achievable rate. So that's a definition. And this is one notion of quantum capacity, but this is the standard notion. This was defined by Schumacher many years ago. I guess also Peter Shor was the first to put forward the notion in his paper on quantum error correction. And I would say this is the notion that's relevant for both communication and it's relevant for computation. There have been some recent works that link computation fault tolerant computation and quantum capacity, and we cited them in our paper to underscore the relevance of this notion of capacity, not only for communication, but also for computation. Another scenario of quantum capacity that's, I would say, maybe more relevant for communication, but again, you could also argue that it's relevant for computation, is this notion of quantum capacity assisted by classical communication. So here, the scenario is we have Alice and Bob in different physically distant laboratories, and before and after every channel use, they're allowed to perform local operations in classical communication. So this means Alice can do a local computation, send some classical data to Bob, who could store qubits in a local memory. This is a local quantum memory. This is of Bob. This is a local quantum memory of Alice. And then there's one mode that she'll send through the channel. Bob will get it. Then they'll again do some LOCC processing. This process will continue for little n times, and then that's the means by which they'll produce the state eta, okay, which is the approximation of the desired entangled state. One thing that can be argued is that this scenario is actually a special case of this scenario. And why is that? Well, the first thing that Alice could do would be this encoding, send one mode through this channel. Then she could store these locally. Bob would simply store this in a memory. Then Alice would send the next one over the channel. Bob would store in a local memory. That would repeat. And then at the end, Bob would take all the systems in his local memory and do a decoding. And so that's a rough argument for why, I don't know if it's written here, the LOCC assisted capacity is never smaller than the unassisted capacity. And it's kind of intuitive that the resource of classical communication can only help to achieve a higher rate. Okay, and that's a reasonable model for communication today because classical communication is much, much cheaper than quantum communication. Okay, there are other notions of capacity, which are the private capacity. And the idea there is each of these channels model what gets transmitted from Alice to Bob. You know, every channel a fundamental notion in quantum information is that every channel can be purified to a unitary acting on a larger Hilbert space. And then the reason the transformation is non-unitary is because we take a partial trace over what the environment gets. In the model of private communication, we can think of the environment kind of like as an active player, as an eavesdropper who gets these quantum systems that are somehow not available to Bob. And then the goal of private communication is to communicate a classical message such that Bob can decode, but Eve cannot. Okay, and so if Eve cannot, then the message being transmitted will be private such that Bob can decode it, but Eve will not be able to figure it out. And it's been known that there are strong conceptual connections between private capacity and quantum capacity. That is to do with the no cloning theorem. Okay, and relevant for quantum key distribution is this model of private capacity, where the communication is assisted by classical public communication as well. Okay, and so things are known like the quantum capacity is less than the private capacity, And the two-way assisted quantum capacity is less than the two-way assisted private capacity. For certain channels, they're equal, but there are known examples where they're different as well. Okay. And then there's something more technical called the strong converse, which I'm not going to pay attention to as much in this talk. It says that these are rates that are achievable if you don't make a constraint that the error is going to zero. You just demand that the error is converging to some number strictly less than 1. And so those are of interest in information theory as well. And we studied them in our paper. Okay. So the problem that was set out in this paper of Zhang and Chen over a decade ago was to compute these various capacities for the bosonic dephasing channel. Okay, and so you see that there's 8 of them, and what we show is that for all of them, they are all, for the bosonic dephasing channel, all of the capacities are equal. You know, all of those different inequalities collapse to a single equality. And the formula that we obtained for capacity is nice and simple. So this was very pleasing from a theoretical perspective. A way that you can interpret this formula is, I don't know if it's written here. Yeah, here's a way to interpret them. This formula, so let's unpack it. This is log base 2 of 2 pi minus a continuous analog of entropy called differential entropy. And this you can rewrite in terms of relative entropy. And I think this gives a nice way to interpret this, this capacity as well as the channel, what's going on. So you can write it as relative entropy between the distribution describing the channel, oops, and the uniform distribution, okay? So it's worthwhile reflecting on the uniform distribution, what's going on with this channel. Okay, so for that, let's backtrack a bit. Yeah, this should do it. So if we plug in the uniform distribution here, you then see that this is a Fourier integral, which is nice and simple. If this is uniform, the Fourier transform will be a delta function, delta n, Kronecker delta n and m, right? And so the Kronecker delta is equal to 0 if and only if n and m are different, right? And so what that tells you is that if the distribution is uniform, that is the worst case scenario for sending quantum information. In the density matrix, if the channel is the uniform dephasing channel, all of the off-diagonal elements will be eliminated. They will be nulled out, and you'll just be left with the diagonals. And so that means, relating to what I was saying earlier, all of the superpositions, all of the coherence terms will be lost. So you'll have no ability to send quantum information. And so for the uniform dephasing channel, the capacity should be 0. Okay, and so we see that with this formula. Why do we see that? The relative entropy is 0 if and only if the 2 arguments are the same. And so, you know, if this distribution is the uniform distribution, the relative entropy will evaluate to 0. And conversely, if this formula evaluates to 0, then we can conclude that the distribution is the uniform distribution. So what that's also telling you is that if the distribution has any difference from the uniform distribution, then you'll have a strictly positive capacity, okay? And the relative entropy is always non-negative as well, okay? So that's the main result. And, you know, that's what was very pleasing from a theoretical perspective. all the capacities collapse and we have a nice and simple formula. Okay. Are there any questions at this point? It might be a natural time if someone has a question. I mean, there's more I want to talk about, but this is really kind of a main, we've gone over a lot with respect to this work.
You can unmute and ask questions if you have. Mark, very nice. These non-Gaussian channels model typically what kind of physical systems? Superconducting circuits.
Oh, it can model any kind of dephasing going on in bosonic systems. So what's very interesting, and we discuss in our paper, is superconducting circuits encode bosonic quantum information. Ion traps encode bosonic quantum information in phonon modes. There are some people trying to do experiments where the quantum information is encoded in the phonon degree of freedom rather than the sort of atomic degree of freedom. Of course, in optical photonic quantum systems, those are bosons as well. And so this channel can describe a variety of systems. And so, whenever you're encoding quantum information in these systems, you're limited by this result. This is the ultimate rate at which you can protect quantum information encoded in bosonic systems when they're subject to this dephasing noise, which is a common kind of noise. So we gave a sort of general model of dephasing, and it would be interesting for these individual systems to describe like what exactly is the kind of noise channel. What is the probability distribution P of phi for particular physical systems?
That's right. Very interesting and very clean result, this relative entropy result of yours. I think, as you mentioned, it solves a problem that was stated in 2010.
Yeah.
So I think if there are no questions, we'll move forward. But just to repeat what you said, Nature Photonics paper got published this year, last year, May, right?
Got published this year in March, maybe. Yeah.
Okay.
So
I think
Ludovico visited Louisiana for 2 weeks in March of last year. We worked on this problem and then we solved it.
Excellent.
So let me continue and give you a sense of
please.
how the results, how we prove the results, because there are some techniques that are useful to know about that could be helpful in solving future problems. There is a multi-mode generalization of our results, right? So now rho could be a little m mode bosonic quantum state, and each of the modes can undergo dephasing according to different parameters phi. They're collected together in an m-dimensional vector phi, okay? And then what we find for this case is something very similar. It's essentially the same thing. Relative entropy between this distribution and the uniform distribution on little m modes. And, it's the same thing, all the capacities, the 8 different ones that we mentioned, collapse to the same value. There's this technical condition, but this is going to be satisfied for distributions of physical interest, I would say. Okay, and one thing that should be stated is that there's a finite dimensional dephasing channel that can be studied, and this generalizes that as well. Okay, so actually this is still giving you more sense of the results. Different regimes. So we talked about the the bosonic dephasing channel with the wrapped normal distribution. That's the one I'd say is of most physical interest because the channel can be derived from a particular Hamiltonian interaction between the system of interest and the environment. And that Hamiltonian is described in the paper of Mancini, I believe also in the Jiang Chen from 2010. Okay, so for that channel, this plot is showing you quantum capacity or rate, in fact, for all these different capacities, rate versus the dephasing parameter. So what do we expect if there's no dephasing? Then the capacity is actually infinite. There's no limit because you can encode an infinite dimensional quantum state and have it preserved. And an infinite dimensional quantum state can encode an infinite number of qubits. So if as the dephasing goes to 0, the capacity goes to infinity. Okay, but then as the dephasing increases, the channel, if we go back, if we think in terms of the wrapped normal distribution, that was that, I'll just go back to it. There was that figure I had that Ludovico made, this one. So if the variance is approaching infinity, then the probability is just sort of randomly distributed around the whole unit circle, right? So and then it's actually uniformly distributed. So the wrapped normal, in some sense, converges to the uniform as gamma goes, as the dephasing parameter goes to infinity. And as that happens, we argue that the capacity should go to 0, and that's reflected in this plot. Okay, so you see that, and then you might wonder more precisely, well, if we expand for small gamma, what does the capacity look like? This is a precise formula. So it's increasing only logarithmically in terms of the inverse dephasing parameter. And as the dephasing is large, the capacity is decreasing exponentially. So those are some interesting expansions. And this can be, again, it's for the different capacities, qubits per channel use or private bits per channel use. Okay, so what are the ideas? So for this, I have extended the talk to occupy the full hour, I guess. And at any point, if there's questions, please interrupt. So to prove this result, we're going to focus on the quantum capacity. We argued before the quantum capacity is less than the LOCC assisted capacity. So to establish equality, we can prove a lower bound on the quantum capacity, and we can prove an upper bound on the two-way assisted quantum capacity. And then in the paper, it's argued how this applies to private capacity as well. Okay, so to get the lower bound, we can invoke known results due to Seth Lloyd, Peter Shor, and Igor Devatak in years that were almost spanning a decade. One could ask why there were these different papers appearing over the span of a decade. There was Seth Lloyd put out his paper and had a particular method of encoding, decoding, and maybe some technical details of the proof were not clear. Peter Shor delivered a lecture about it, but never published a paper. He had a different method. Several years later, I think in 2008, Andreas Winter and Patrick Hayden published a paper with him talking about more of the details of the method, working out a detailed proof. And Igor Devatak had a completely different method that was related to private communication. Anyway, all of these results together, they pinpoint a quantity called coherent information, the difference of the entropy of Bob and the joint entropy of Alice and Bob as a lower bound on the quantum capacity. So what you do is you send in some state to the channel. You send in a bipartite state. You then evaluate this entropy difference, and you can optimize over all possible input states. And these theorems prove that this formula gives a lower bound on the capacity. This formula was conjectured by Schumacher prior to the work of Seth Lloyd. Okay, and then for certain channels, which are called degradable, the quantum capacity is equal to the coherent information. And we actually know, due to this property of the bosonic dephasing channel being a Hadamard product, which I talked about previously, that it has this degradable property. So we know that the quantum capacity itself is going to be equal to the coherent information. But still, we're trying to prove a lower bound, and so we don't necessarily need this equality, but it's something that does hold for this case. So what do? We do what you might consider a very simple idea. We choose as the state to send into the bosonic dephasing channel a maximally entangled state of largest photon number D. Technically, I think there's a slight typo. I think this should go from K go from 0 to D minus 1. I think we need to include the vacuum for this argument. Maybe for a technical reason we wouldn't need to, but at least in the paper we started from the vacuum up to photon number D minus 1. So we send in that state, and then when you work out the formula for coherent information, it will work out to this expression where we talked about the matrix induced by the channel previously, this Toeplitz matrix TP. The matrix that appears in this formula when you send in the maximally entangled state is the upper left D by D block of the channel matrix. And so that's kind of interesting. Using the maximum entangled state, you can extract the upper left block of the matrix describing the channel. Okay. And as we said before, this is a Toeplitz matrix. Okay. And so then to evaluate this formula, which kind of looks like an entropy, you need the eigenvalues of this matrix. And so we're left with a mathematical puzzle. How do you compute the eigenvalues of this matrix, right? And as an example of a Toeplitz matrix, this is what an example would look like. We said that the entries were constant and depends only on the difference of the indices, right? So the difference of these indices here is 0. The difference of these indices is 1. And so you have these this diagonal form, okay? So this is actually not so easy to diagonalize. However, if B is equal to C, the matrix is said to be a circulant matrix, okay? Which is kind of a finite dimensional version of a Toeplitz matrix. And in that case, the matrix that diagonalizes a circulant matrix is the discrete Fourier transform. And so this is some kind of hint as to how to proceed with diagonalizing these ones, okay? Okay, so this is giving some further hints of what to do. Let's see. So in the case that P, the probability distribution is supported on just a finite number of points that are evenly spaced around the unit circle, then this matrix, the one that wants to diagonalize, becomes circulant with these eigenvalues, okay? And then in that case, this formula that we want to evaluate will be equal to the difference of logarithm of the Schmidt rank D of the maximally entangled state and the entropy of this distribution. So this is giving some kind of hint as to how to do it. But the question is, like, when D is going to infinity and we have a continuous probability distribution, what to do? So for that purpose, we invoke this powerful theorem that mathematician named Sago came up with in 1920, and then there were further refinements of it. So what does it say? If the probability distribution you're interested in satisfies this technical condition, which we said would be satisfied for bosonic dephasing channels of physical interest, then if you have this kind of expression where you have the trace of a function of the templates matrix you're interested in evaluating and normalized by D, then this expression will converge to this one, where you just take the function of interest and plug in the probability distribution and perform this integral. So that was the key theorem needed for the lower bounds, and the function of interest for us is x log x, right? That was the function we had previously, x log x. So it's precisely the right tool to use to solve our problem. And then when you evaluate this integral for the function x log x, you'll get the formula that I stated earlier. So that's essentially the proof of the lower bound. Why is this a lower bound? Well, we could use a maximally entangled state of Schmidt rank D as the state to choose for any integer value D, right? Any integer value D gives you a lower bound. And so then we're allowed to take the limit as D goes to infinity. Okay, so the statement here is that in principle, this is what you could achieve, but performing an experiment to demonstrate this formula would be extremely challenging and probably beyond the reach of current experiment. Maybe there's ways that you could approximate it with certain techniques. Okay, so I have 8 minutes. Maybe I should try to quickly go through the proof of this upper bounds so that there can be a little time for questions. The upper bounds, we said we're going to bound the two-way assisted quantum capacity from above by this formula. Okay. And then the two-way assisted capacity, it requires an optimization over this class of like complicated protocols. So one thing we can prove is that the channel, the bosonic dephasing channel, falls under a class of channels that are said to be teleportation simulable. I don't know if we have a figure to describe this. We don't. But what it means is that by means of if you feed in a maximally entangled state of dimension D to the channel, that is a state that encodes everything about the channel. Okay, and to make this precise, D needs to get larger and larger. Okay, but this channel has sufficient symmetry such that you can perform the usual D-dimensional teleportation protocol over this channel, and using this choice state as the resource state rather than the standard maximally entangled state. And then the whole process simulates the channel up to an error that vanishes as D goes to infinity. And so that allows you to rewrite such a complicated protocol in terms of a single LOCC using little n copies of the choice state as a resource, okay? And so that concept was first put forward very insightfully by Bennett, DiVincenzo, Smolin, and Wooters in 1996 in their famous paper on entanglement theory. And then it's been increasingly developed over the years since that time, and in some instances rediscovered. Okay, so the idea there is the teleportation simulability of the channel implies that the distillable entanglement of this resource state is an upper bound on the two-way system capacity. That's the key thing. And then we can use as an upper bound on distillable entanglement an entanglement measure called relative entropy of entanglement. And then we make certain choices for the relative entropy. I'm not giving the detailed definitions here, but the relative entropy of entanglement involves a minimization of the relative entropy of this state over all separable states. So we make a certain choice of the separable state, which is actually, we just plug in the dephased version of this maximally entangled state. And then this formula collapses to the same one found in the lower bound. And then we take the D infinity limit, and by the same argument, we get the same formula. So, to prove this, we use the Sago theorem twice. That's the key idea. In summary, we have this nice formula. We use techniques from complex analysis involving the Sago theorem. We employ this concept of teleportation simulability. In our development, we made no physical constraints on the energy of the states allowed for communication. In practice, there will be energy constraints that motivates, defining and understanding the energy constraint capacities. That's something that's open. Another thing of interest for any physical system, including ion traps, superconducting, photonic, is what if there's loss? So you can compose the bosonic dephasing channel with a pure loss bosonic channel. Maybe that's the ultimate bosonic channel to consider. There are other ones with thermal noise as well, but this would be upper bounds on it, that's an interesting question. So that's all I have. Thank you for this opportunity to speak.
Thank you very much, Mark. Very clear and very interesting presentation. We have a couple of minutes left, so any questions, comments? Please feel free to unmute yourself and ask your question.
Actually, I have a question, sir.
Yes, please, go ahead.
How did you calculate the degradability of this channel?
Okay. So we proved that it's a Hadamard channel, right? That was sorry, it's going fast. That was this statement here. It's a Hadamard channel, and in my book, Quantum Information Theory, there's a section on Hadamard channels, and what you can prove is that the map from the input to the environment is an entanglement breaking channel, and degradability means that there'll be a channel that maps the Alice Bob channel to the Alice Eve channel, and that's the short argument. But in the book, you can find a detailed proof of degradability of Hadamard channels. So Hadamard channels, I would say they're on their own, they're an interesting subset of degradable channels. For those, a central result is that this is something I did a decade ago. There's a capacity region of what you could do with classical communication, quantum communication, and entanglement assistance. And that whole region is fully characterized for Hadamard channels. That's something we did not do in this work, but it could be done. That's another interesting question that I didn't that I didn't list. What is the capacity region of the bosonic dephasing channel with no energy constraints? That might be something to solve. That could be interesting in future work.
Thank you.
Any other quick question, comments?
Yeah, I have one
Yeah.
quick question. Mark, just
Hi.
a quick thing. So these channels are all infinite divisible?
Sorry, the audio was choppy.
Okay, so is this channels are all infinitely divisible?
Infinitely divisible. They form a semigroup, right?
Oh, then it will be infinitely divisible, right? Markovian, it would be, right?
Yes, yeah, you can describe, I believe it's correct, and I think it's discussed in the Mancini paper, that you can describe them by the Lindblad equation,
Mhm.
where the Lindblad operator is the photon number operator.
I see.
There's
It is
just
for
single
it is
one.
for any mode, right? Any mode you can any mode Gaussian channel you can
This
do
would be
that.
the single mode bosonic dephasing channel. There would be a dephasing rate, let's call it lambda, that would be related to gamma in some way. And then it should be possible. I would think the multi-mode bosonic dephasing channel would be described by Lindblad. There would be M Lindblad operators, each of which is the photon number operator acting on the ith mode.
Just a curious thing, if I can ask, just is it true for
Yeah.
any Gaussian channel or not? Or maybe we can
Oh.
continue later.
That's an interesting question. For any Gaussian channel, is there a Lindblad description?
Maybe I can discuss it with you later, Mark. I can drop a mail to you because I
Okay.
have a question which I didn't fully understand actually.
Okay, I
Very
think,
fine.
I suspect that that's true. I know it's true for simple channels like thermal channel, amplifier channel, loss channel, additive noise channel, but for a general Gaussian channel, I would suspect that is known, but if not, that's someone, you should write a paper about that.
No, there is actually a reference on Hinosari, Holevo, and Wolf's that original paper,
Okay.
but they were mostly considering the single mode and then slightly. I mean, I was not very comfortable with the understanding the logic
Okay.
there, and so it was not very clear to me. And anyways, we can discuss it over
On
mail.
this
I think.
interesting note, I think we come to a close for this talk. I would strongly urge Rita to get in touch with you, and maybe it would continue. This conference is actually a series, has been doing very, very well. So let's all thank Mark for this very interesting and wonderfully presented talk. Thank you very much.
Yeah, I'm here.
Professor Agarwal. So nice.
Yes, yes.